Lunchtime Research Faculty Presentation Series on behalf of the Percy Wooten University Research Center. I am going to be introducing our speaker today. So Dave Hobart is an assistant professor of chemistry at the University of Lynchburg, where he teaches analytical, environmental, inorganic, and forensic chemistry and mentors undergraduate research students. His group studies transition metal coordination compounds with applications in catalysis and biology. Before joining Lynchburg in 2022, he held visiting faculty appointments at Virginia Tech and Radford University and led projects as a Senior R&D Chemist at Air Liquide Advanced Materials, experience that informs his teaching and research methods. He earned his Ph.D. in chemistry from Virginia Tech with Joseph Merola, focusing on the synthesis, structure, and catalytic behavior of palladium amino-acid complexes. His publications include articles in, and some of these I think he included, so I'd have to say them out loud, Molecules, Catalyst, Crystals, Inorganica Chimica Acta, Acta Crystallographica, and the Journal of the American Chemical Society, including work on metallofullerene MRI contrast agents. Recognition for his teaching and research includes Virginia Tech's Favorite Faculty Teaching Award and the College of Science Outstanding Graduate Student Award. He is active in the American Chemical Society, recently serving as chair of the Virginia Blue Ridge section and advises the University of Lynchburg Chemistry Club. So please welcome Dr. Hobart as he speaks to us today about precious metals, uncommon partners, new approaches in coordination chemistry.
All right, so I'll try to speak into the mic. So for those of you who've seen me around, today is proof that I do own something that is not a chemistry-related t-shirt. So this is the one time for your So, let's see if this is going to work. So we're going to have the words precious metals pop up from time to time. So when I say that word, what pops into your head? Everybody probably has a little predefined thing. You think, queens and kings of old and jewels and crown on their head and things like that. If you're a little bit more technically inclined, maybe the catalytic converter in your car, full of precious metals. Silverware, right? Something, again, going back even into antiquity. If you've ever seen the backside of a circuit board, right? Typically they're green or black, and you see all that yellow stuff all over, that's all gold, right? So those are in pretty much every electronic device that we have. And if you are like me and are a certified nerd, something like Iron Man, right? The little arc reactor in his chest, powered by palladium, which you're going to hear all about today. So, be like me. All right, so what do? Basically, it's really straightforward. We're synthesizing new complexes. And I sort of take the shotgun approach. If it looks interesting, I'm game to do it. So what do we got? You hear these words, organometallic. What does that mean? All it means is we're taking a central metal atom and we're bonding some organic stuff to it. That's different than what you might see for organic molecules, sugars, and starches, proteins, things like that. And those typically behave as either a catalyst for something, or what we've discovered in the last 50 years or so, some of those are biologically active and can do some good stuff for us. So you've got a few examples here. So cisplatin on the right, that's an anti-cancer drug. Some of the compounds that we'll talk about later in the talk are biologically active against things like MRSA and tuberculosis and some other horrible things like that. And then nobody knows what that is on the end. It's ferrocene. That's the first real organometallic compound that was discovered up at Hobart. All right, so where we're going to be today, if you go back to high school for just a minute, right? Everybody kind of cringes. The non-science folks kind of go, when I put this up here, periodic table. So we're kind of in the middle where things are flashing. Palladium, platinum, and gold is where we're hanging out. If I get sidetracked, I'll start talking about rhodium and iridium, and I'll try to avoid that for you guys. So we're gonna kind of hang out in the middle of the table, and that has some advantages for what we'll talk about there. All right. So we had an unusual start. We say I had an unusual start to this. I went back to grad school as a bit of an older student. I was 38 when I went back, and so you get into there and you figure out what am I going to do. And for where we were in Virginia, down in Blacksburg, that might not seem too weird of a thing, but that's how I got started in research, was working with some NASCAR folks. Why NASCAR? It's all about, if you're into car racing, right, it's all about fuel economy on the track. And so if you can do something to the car or whatever to buy you some time back, that can be worth literally tens or even hundreds of millions of dollars in prize money and endorsements and sponsorships and things like that. So there's a huge push for these guys to figure out, well, how can I make the car run better, okay? And so it's all about fuel economy. There was one gentleman in particular, if you know anything about NASCAR and know who that is, Richard Petty, right, in the number 43 car. And on the back end of the fender, you see STP. So STP is a fuel additives company, and they were the ones that were really kind of invested in this thing. Like, how can we make this work better? Well, you can't take a metal like palladium, and you can't make an engine block out of it, right? Because you want to improve your combustion efficiency and things like that. If you did that, how much do you think the engine would cost? Each car engine would cost about $13 million to build it, to machine it out of palladium. You can't do that anyway because it doesn't have the materials properties that we need. And even if you could, even just doing the pistons would cost you 140 grand per car. And then consider that for most of those cars, they swap the engine every race. Like, they run the daylights out of it, and then they go, okay, Daytona 500 is over, engine out, new engine in. So those obviously are completely not realistic things to do. So the STP folks and whatnot said, hey, what if we put something in the gas? Because that we can handle, right? You stir some stuff in and it makes it work better. And so, and I'll apologize to the folks that are not chemistry folks, there's going to be lots of stuff like this today. So we come up with a compound, we said, hey, let's get the metal into the gas. So how do we do that? We stick some of our organic stuff on it, and it turns out that that's soluble in gasoline, and when you put it into an engine, it improves the fuel efficiency of the car by about 12%, which is fairly significant. It's terribly expensive, right? So we had this idea early on that, like, this wasn't going to be something that you might go to Advanced Auto Parts and buy, cartons of it and pour it into your Honda. But for the NASCAR folks that are talking, hey, we can earn $100 million in prize money, spending $80,000 or $90,000 on a fuel additive, maybe not such a bad idea, right? Return on investment. So we start coming up with stuff like this, and we do this, we set up a testing lab, and we're making new compounds, we're doing all the fun stuff, and then life happens, right? And by that I mean the CEO of the corporate sponsor took all $550,000 of our startup project money and absconded overseas with it, and a year and a half of my doctoral research. So we kind of let the dust settle from that. I don't think he's, to this day, ever been brought up on charges or anything. He apparently, I have to be careful what I say because I'll get sued. He fled to a country with whom we have no extradition treaty for financial crimes. So he's living large on $500 million overseas, while I was getting 20 grand a year as a stipend, eating ramen noodles and beanie weenies to get out of grad school. So we said, all right, we gotta figure out how can we turn lemons into lemonade. And it turned out to be not as bad as one might think. So in doing all of the background work and whatnot, we had found a lot of this, most of this background work was done in the 50s and 60s in our former Soviet bloc countries. So the Soviet Union, East Germany, Poland, places like that. And to be perfectly honest, there was a lot of mistakes in it. There was a lot of really sloppy science. For my science folks here, examples would be like taking one infrared spectrum as proof positive that I've made a new compound, and then publishing it in the literature, right? They would do stuff like that. They're like, no, we can't do this. So we had loads and loads of evidence of that going on. So we already do a bunch of palladium stuff. So we started in on a project. We're gonna go and redo all of that work. We're gonna do the document the synthesis. We're gonna characterize it using 4, 5, 6 different techniques to make sure that we actually did make the stuff that we said we were making. It's just good, basic, fundamental research. And so I'm going to also try to tie in for my students, like why is this important for you guys? Because doing good research can just be basic stuff. It doesn't have to be super sexy or cutting edge. It's always nice if it is, but you can do good science and make a contribution by just doing good, basic, fundamental work. So that was really where we landed and said, okay, I can take what I know, I can expand on that, I can get out of grad school and make my way ahead. It also was fortuitous for us that palladium in particular was a pretty hot topic at the time. This was 2008, 9, 10, and in 2010, the Nobel Prize in Chemistry went to the guys who invented palladium catalyzed cross-couplings. So everybody, it was like, hey, we want to get on the bandwagon. And we noticed, as you're reading all the papers and you're doing all this stuff, like, hey, their stuff looks a lot like our stuff. Or, as my research advisor told me, go the other way. Your stuff looks like their stuff, because they're the important ones, because they got the prize. So we said, hey, if their stuff catalyzes reactions, maybe our stuff does too. And so we had another place to start looking at what do these compounds do, what might we be able to turn them into. And we also knew that some of these metal compounds at this point were pretty potent anti-cancer things. So we were always looking for like a biological edge. You can collaborate with your biology colleagues. So how can we make this work? So that was another avenue. So when I say the shotgun approach, right? We've got all these compounds, we've got a couple, 4 different metals we can play with, and we can do a bunch of stuff with them, right? We can do basic research, we can do catalysis, we can do bio stuff. So it gave us some options. All right, so we do have to have a little bit of chemistry class so that you kind of see where we're going with this. All right, so when you put 2 things on a metal atom, they can go on in two different ways. And this is a little bit of an oversimplification, but here we go. So if I put things on the metal to where they're on the same side of the metal, they're next to each other, we call that cis. And if we put them across from each other, like reaching across the Thanksgiving dinner table, right, that's called trans. And so for the type of chemistry that we're doing, all of our metal systems are what's called square planar. So they do look like this. You have a metal in the middle with 4 bonds coming off of it. And so it matters which one we make. And it turns out to be critically important for certain things. What we really want is that cis. That's the ideal case. Now, you probably have a pretty good guess that you can't just say, well, because I want it, I'm just going to make it. Right? It doesn't often work that way. So one of the first things we have to do is figure out, what's that actual connectivity of the atoms? And that's what's hard to do. And we'll get there as we start talking through some of the more interesting stuff. But we really want to make cis. All right, so to do that, what are we going to start with? Well, you're going to start with the simplest thing you can get your hands on. So we started we said we're going to focus on amino acids, because also at the time, things that were biologically relevant were important. So we said, okay, what's biologically relevant? Amino acids are. They have a nitrogen on one end and they have an oxygen on the other end, and those can reach around and they can stick onto the metal and they can hopefully do some fun stuff. So we start with glycine. That's the simplest thing there is, and the idea behind this was, again, for my students, this is great. There's nothing crazy about this. It's just good, basic, like you gotta know your stoichiometry, you gotta know how to balance an equation, all of that simple stuff. So we do this reaction, and the other nice thing about this from an undergraduate research standpoint is, if you think back to the periodic table, all of that stuff in the middle, a lot of that stuff you can't do in air, right? It's air sensitive stuff, so you have to do it in special apparatus and glove boxes and shrink lines and all kinds of fun stuff, which you don't even have to know what the words mean. But when you think about special apparatus, what's the first thing that pops into your head as a principal investigator? Exactly. Those things cost money. Like a glove box costs $150,000, which I don't have. Okay? Shrink lines cost $1,000 a pop, and every student needs one. So we wanted to look at some things where, we're just getting into this, and it's like, hey, let's do this, not on the cheap, but we want to be reasonable on how we take this approach. So we said, fine, we're going to go grab some glycine, we're going to take our starting metal materials, we're going to mix them together, and we made this. Now, how do I know I made that? We're going to get there, but the other nice part about this, again, to tie this for undergraduate teaching, is you start off with a solution that's a deep red-orange, you do some stuff, and you come back the next morning and you look at it and it's turned into this brilliant yellow solution with some yellow crystals at the bottom of which is nice because you can immediately tell, hey, something happened, right? We clearly did something. It went from this color to this color. And like everywhere else in the world, right, if it goes from red, orange to like brown or black, that's probably not good. It's typically browns and blacks in metal chemistry, or means you've made garbage. So the fact that we have this lovely, brilliant, vibrant yellow, whatever, it's like, good, something did something. And then you open the flask up and you get blasted in the face with the smell of vinegar. Which is also like if you open up your wine bottle and you get blasted in the face with the smell of vinegar, something probably went wrong. In this case, nothing went wrong. This was fantastic. So the students start to learn like, hey, you know what? Just simple observational things, color, smell, what is it? These things matter. You should be jotting these down and figuring that out. So I've drawn this up. So if you think back what I said, I drew this up as trans. Well, I said that's not what we want. We don't want trans, I want cis. But you get what you get and you don't throw a fit. And we didn't know that at the time, right? So again, we first come in that next morning, it's just, hey, it's gone from red to yellow, something happened, now we got to dig in and figure out what we're going to do. So what's the first thing you might want to ask yourself? Did I actually make what I was trying to make, right? I want to look smart. Did I make what I hypothesized? So how do we do that? So now we start getting into some of the characterization techniques. And so I'm going to go through a list of these, and it's not super important that you know all of these, but they're kind of in order of what we do. So the first thing I'm going to do is we're going to send this down to another lab on campus, and we're going to do some high-res mass spec. Okay, and we still do this even for the work that we have here. Again, most of these things are hundreds of thousands of dollars in equipment costs, which we don't have here. We don't have the infrastructure for them here, even if we had the cash for them. So we can send these down, and it would cost you $22 and you get a mass spec. That's fantastic. So students are prepping samples and we send them out. So what does that tell us? Mass spec tells us the atomic mass of the compound and the isotope distribution of what we've made. So I'm going to show you an example of that in a minute. You'll see what that means. So you get an immediate hit on, did I actually even make the thing? That's important to know, because if you didn't, there may be no point in continuing. Then we need to figure out how are the atoms connected. Okay, so then we go down to another lab on campus and we say, hey, we can grow crystals of this stuff, and we can put it in the instrument, and we get a crystal structure, and that tells us how the atoms are connected. All right, we go down to another lab and we do some nuclear magnetic resonance. That tells us about how many different kinds of a thing are there, how many different kinds of carbon are there, how many different kinds of hydrogens are there, things like that. And then we get into some other stuff, which I can kind of buzz through here. We do some GC work, we do some basic spectroscopy. We send it out for elemental analysis, because even today, with all of the other high-tech stuff that you have available to you, if you go to publish your work in the literature, all of the journals require you to submit an elemental analysis for a new compound. So you have to go calculate and say, hey, again, this is basic Gen Chem stuff for my students, right? But you got to go calculate and say, hey, it's X% carbon, it's Y% nitrogen, it's Z% oxygen, and it's got to match up to within error of the calculated theoretical value. So you still have to do that. So we send those out, and then we go and hang out with our biology friends, and we're starting to do some biological activity testing and some to figure out if these things kill bugs or the anti-cancer compounds. So there's this the Kirby-Bauer disk diffusion test, which we may talk about later. And then the fun one, I think, is this NCI-60 human tumor cell line test, which is an anti-cancer screening run by the National Cancer Institute. You submit your compound structures to them, and if they're accepted, they will say, yeah, hey, send me 100 milligrams or 150, whatever it is they want these days, and we will assay that against 60 different cancer lines, and then send you back a report that says, hey, you know what, your compound was not active, or hey, it's good for breast cancer but not for testicular cancer, or it's good for colon cancer but not lung cancer, whatever it happens to be. So obviously they were shut down. During the shutdown, they're just coming back online. And to get to here, the reason this is at the bottom, they will not even consider looking at a compound if you don't know the structure, how the atoms are connected. So that becomes very important. We can't just say, hey, I think I made this. Do you guys want to check it? They're going to be like, nope, you've got to prove that it is what you say it is. So that's why that's the last thing we do. And it's been a minute since we've been able to send them anything, because we're still waiting on crystal structures for a lot of the stuff that we're going to talk about. All right, so we do all this stuff, right? So again, you can start to see, like, it's not just as simple of you know, we make jokes about, I go in the lab and I mix a little of this, a little bit of that, and whatever, and I'm a chemist, that's what I do, right? That's the easy part. And then all of this other stuff comes in, and this is what takes years to get done, right? I made 37 compounds for my doctoral dissertation. I made 37 compounds. I had all 37 of them synthesized in about 6-7 months. It took 5.5 years to get all the rest of the data, to be able to put it into publication and send it to NCI and do things like that. So that's where the grind comes from. That's where the hard stuff comes in. All right, so let's go. We're going to go pick on that first compound that we made, and we're going to go look at its mass spec. All right. So did we even make what we said we are going to make? And I'm bringing these up. You're like, well, why are you talking about stuff you did back in grad school? Well, because I could, but also because I typically have my students do this as a first step because we know exactly what it should look like. It kind of gets them into the groove and get their hands wet. They can do some things. So again, step one, did I even make what I said I was going to make? Well, how do we figure that out? Throw it in for a mass spec. So what you get is a little plot looks something like this. And if you notice all the lines on there, so in this case, this is a palladium compound, right? And so you go to the literature and you say, well, palladium has 6 naturally occurring isotopes. So every time I make the compound, the central atom in that is one of those 6. So when I look at the spectrum of the sample as a whole, I should see all 6 of those in there. In fact, you have to see all 6 of them in there. And they have to be present in a particular ratio. And if they're not, then you either have a mixture of something, which typically doesn't happen, or you didn't make what you thought you made, right? If I got no reaction, I would see the glycine off somewhere else by itself. I wouldn't see it stuck to the metal. I would see the metal by itself, not stuck to anything else. And so this is a really easy thing to do. You literally take down just a few drops of the material, they stick it in there, boom, and within an hour you know what you got. I don't know what that was. What's that? Interesting. So you know what you got, okay? Nice and simple, and then that tells you whether it's worth going on and doing more work. So how do we know we got this right? Well, there's online calculators. You stick your molecular formula in there and says, hey, this is what you should see. And so you'll notice these look pretty good. There are some slight discrepancies because of the way that the calculated version gets done, but you can see that the 6 isotopes are there. I've got my 6. Everything looked good. So we come out of that one within a couple of days of actually getting in the lab and starting the project. Yes, we made the compound, okay? I still have no idea whether it's cis or trans, and that kind of is important, so I want to figure that out. So then we start the fun stuff, all the rest of that list. So what are we going to do? Well, we got to grow a crystal. Who thinks that might be easy? No, it's not easy. So this is the fun part, and your students look at you like you're an idiot. You take a little vial of the material, right, and you take a saturated solution of it, and you filter it, and you stick it in the vial with a label, of course, and you put it on a windowsill, and you go away for 3.5 years, or 6 months, or however long it takes, right? So the water starts to evaporate, the solvent starts to evaporate, you go from saturated to super saturated, you finally get some crystals, you go, woo, and off you go. And then you're cooking. Sometimes you can get a crystal within a couple of weeks. Sometimes it takes 4 or 5 years. I've literally got stuff that I brought from grad school. I kept with me while I was back working in industry for a few years. Brought them with me here. There's no safety and ocean people here, right? They're just little tubes, right? And they're sitting in the lab in a little thing, and I'm still waiting for them to crystallize. They still haven't done it. And it's been a minute, right? So it's going on, what, 10 years? Yeah, something like that. Some of these cases, 10 years and it hasn't crystallized yet. It can take a while. So, how does that work? Again, this is another $1 million piece of instrumentation. And so you go down to the lab, you go talk to would you believe it's the geology folks that do a lot of this. So all of the X-ray equipment down at Tech is actually housed in the geology department. They do stuff like garnets and diamonds and all kinds of fun stuff. Well, they can do a crystal of anything if you can grow it. So you put it, let's see if this is going to work. So you put your little crystal right in this thing here, right? And so this is the X-ray source, and this is the detector. And it looks crazy because it sits there, and then the whole thing, it looks like a ride at an amusement park. It goes bar, and it tilts, and it goes bar, and it tilts, and this way and this way. So you grow your crystal, that's fine. So then you're shooting X-rays at it, right? And so it has to do an analysis in all, to get the connectivity, it's got to do an analysis in all three axes. So the whole thing is rotating in all these different directions. And to make matters worse, you've got to cool it down to 100 Kelvin, which is minus 280 Fahrenheit, or minus 173 C. So the whole while this is going, there's a little stream of liquid nitrogen blowing on it to keep the crystal cold. And why do we have to do that? Because at room temperature, the atoms are vibrating, and that makes them move enough, even though you think, well, that's a solid, right? It's just a crystal material, but the atoms are vibrating enough that it screws up the calculation. So you cool the thing down. You go do this. It takes about, I don't know, 6-7 hours to collect the data, which is not. Everybody goes, oh my gosh, that takes so long. Why are you hogging up the instrument? Do this. So think of it this way, and I remember this from the news because Crick just passed away, right? So Watson and Crick, DNA guys, right? They do a crystal structure of DNA. How long do you think it took them to do that? About 4 years to collect all the data and solve the structure and do that. You can do this in about 12 hours. Data collection, analysis, the whole thing. And so you go to, you take it off to the lab, you go home and you go to bed, you wake up and there's an email sitting in your inbox that says, here's your structure. Boom. So that used to be like when my advisor was in grad school, one crystal structure was a Ph.D. thesis. I have 37 of them in my dissertation, right? Because it's that much faster these days to show that the computing power was the limiting factor there. So this is now just a routine thing. So this is the second step that we do if we can get a crystal. We throw this thing in there. So we did this for ours, right? Well, you want to know what's happening, right? So the X-rays are going through and they hit the nucleus of the atom, and then it's like, it shoots off to the sides, and that's what the detector is measuring. Like, I know the beam should be coming this way, but I detect it over here. So it does angles and energies and distances, and it can figure out what makes that happen. So all of that's going on, and you get an unequivocal picture of that atom-to-atom connectivity. So we did that for this compound. This one actually did grow a crystal within about a month, so we kind of got lucky. And this is what comes out of it, right? So now we knew, aha, I made, well, nuts. I made trans. I didn't really want trans. I wanted cis, right? But I got trans, so we are going to do some work with that one while all of this other stuff is going on. So remember, I'm kind of focusing at this point in the talk on one compound, but there's about 30 others in the crock pot going on in the background as all of this is going on. So, okay, fine, we made trans, and this is still nice because it's a very, very simple molecule, right? There's only 2 kinds of carbon in here. There's only 2 little protons here. Well, there's 2 more over here as well. These don't really count for reasons that don't matter. So there's 2 hydrogen atoms here. There's 2 carbon atoms. So it's really, really quite simple, which is nice when you're trying to figure out what's going on. So we're going to throw that into the nuclear magnetic resonance, the NMR spectrometer, right? And so for that particular molecule, because there's 2 hydrogen atoms right here, there's 2 hydrogen atoms right here, and they're all the same. So that was kind of boring, right? You look at the spectrum, you go, oh, I got 1 peak, hurrah, whatever. I can't really tell anything. Okay, for my math people, can you define a line with 1 point, or do you need something else, right? You need something else. And so with 1 peak, I can't really do anything. So it's like, all right, the hydrogen one is not so important. Let's go look at carbon, because at least there's 2 things there. I look at that structure and I go, okay, there's 1 carbon, and it's the same as this one, right? And there's a carbon, and it's the same as this one. So there's 2 kinds of carbon in this molecule. And another big thing that comes from this is you have to be able to draw out symmetry in your head, or at least draw it out on paper, because if two kinds of carbon are the same by they're symmetry equivalent, then they show up as the same peak on this type of spectroscopy. So I look at this thing and I go, well, I should have 2 peaks, right? I should have one here for this guy, and I should have one here for this guy. And so we're going to go look at the card, that's called a carbonyl. So we go look at that, and pop up the spectrum and go 1, 2, 3. Even though those look like 2, that's called a doublet, and there's no way to collapse it down. So that is everything that's the same height, right? That's one peak, that's one peak. And this little bitty thing down here, that's one peak. So we're looking at this and we go, well, there's 3 things there. How is that possible? Oh, maybe I have a messy sample. Maybe it's ugly. But then we said, well, you know what? No, because when you made this sample, you got a little bit smart, which means I listened to my research advisor, and I grabbed a pair of tweezers and I pulled a single crystal out of the little flask, and that's what I did my NMR spectrum on. So I know that what I put in the NMR spectrum was absolutely pure. No chance that it was more than one thing. But when I look at the spectrum, it shows me 3 things. And then I go look at the other end, which is those 2 carbons, and I see this. Well, that's fine. I see the same thing. There's 3 different kinds of carbon there. Well, that's kind of cool, right? I made a comment. There should only be 2 kinds of carbon, but for each one, there's 3 things going on, which started to be the sort of the eureka moment. Like, hey, something cool is happening. What's going on? So one of the things that we were trying to do with all of this stuff, we just kind of figured it was a matter of good environmental stewardship or whatever, is we were trying to use non-horrible organic solvents, right? So we said, we're going to do all of this chemistry in water. So, which you can do. So we did all this in water, which was kind of new for some of this kind of stuff, but because it's not air sensitive, it's also not water sensitive. So you can do that. So we were kind of like, we're doing green chemistry, but we're not really doing green chemistry. So we got to thinking, okay, so this is where you everybody, you put your pens and pencils down and you just kind of walk around the lab and you're doing this, and you're drawing stuff on the dry erase board, and you talk to your PI, and you talk to your lab mates, and you go move some things over, and you still get, well, aha, I think I know what's happening. I have an idea what's happening, and that is this. So I think I made this. Well, I know I made that because I got a crystal structure that says I made that. But when I put it in water, the thing opens up. Right? It's like a dry sponge expanding. Right? I put the compound in water, and it doesn't stay stuck together. One end of this little ring decides to let go. And we still don't know to this day. We don't know which end lets go, but we can make a guess, and so we think it's the end with the oxygen is the one that lets go. And so we say, okay, well, that end lets go. And when that happens, now you can justify having 3 different environments for each of your carbon atoms. And so we figured, okay, this has to be what's going on. And it fits. It's like, this is great. Okay, so if I do this, I say it was totally unexpected. It was only totally unexpected because in an organic solvent, that wouldn't happen, right? So what happens is water can actually come in, and water can kind of stabilize it. So like if I'm like this, if this arm comes off, well, the water molecule is going to come stick right here, and so this guy can sit out here and do this, and everything is nice and stable because that water molecule does it. Again, that wouldn't happen with something like hexane or benzene or something like that. So we're sitting here going, okay, well, the fact that I've got 3 means both of the oxygens are letting go, right? So if they were cis to each other, I'd have 2 open sites right next to each other, which would let me do some catalysis, and then we might actually get some money from ACS and PRF and guys like that, which would be great. So we're going to go try to prove that this is what's happening. We're going to go do some catalysis. We're going to just go pick some reaction. But first, I want to go make this cis. Because I get ahead of myself. And I'm like, yeah, we're going to go run this reaction. And my boss is like, wait a minute, what are you forgetting? That's a trans complex. It's not going to do anything. And we did go prove that it wouldn't do anything. But he says, you got to go make this one first. Otherwise, you're just kind of spinning your wheels, and we don't want to do that because palladium is expensive, platinum is expensive, gold is expensive. Gold is ridiculous these days. Right? So we don't want to just be going willy-nilly and doing all this stuff. All right. So what do? Again, for my students, right, we go back to first semester general chemistry, first principles, basic stuff. And we go, all I gotta do is change the starting material. I just use a different palladium salt and it'll work fine. So we switched it from palladium acetate to palladium chloride, did the exact same reaction, bang, cis, worked like a champ. That crystallized in about 2 weeks, got it on the diffractometer, proved it, did the mass spec, proved it. We did the NMR work, you do everything all over again. Shows the same 3 environments for each of the carbons. So we got, hey, the same behavior is happening, but now I've got the right geometry to do this. And so then you realize, ooh, this is just with glycine. I can do this with other stuff that's way more interesting, right? Like proline. We got the way of the poking there. So what's cool about proline, biochemistry students, right? It's got, the right button. It's got a chiral carbon. Now what does chiral mean? All right, this is you guys get to do some fun stuff. Take your hands, right? Put them up like this, turn them sideways. And imagine there's a mirror between your hands, right? So your left hand is a mirror image of your right hand. Okay? So it's a mirror image. Now turn them so say your palms are away, right? And then try to put your left hand over your right hand. Can you do it? And have it match up exactly? Doesn't work that way. So it is your hands are a chiral pair. They are non-superimposable mirror images. Okay? That becomes important later on. So we want to start making compounds that have at least one chiral center in it, because when we're doing catalysis, you can't make a chiral product unless you have a chiral catalyst. So that became kind of cool. So we started doing that even before the ink was dry on the printout of the diffractometer data and the NMR data. We said, let's get cooking. So we said, all right, we've got proline. We can go order all these other amino acid derivatives that also have these ring systems on them. So proline is a naturally occurring thing that's got a 5-membered ring. We went out and got stuff. 5-membered ring, this is the normal one. We found one that had a methyl group stuck on it. We found one that had fluorine stuck on it. That becomes important later too. We found one that had an OH group stuck on it. That was great. And then we found one that instead of a 5-membered ring, it had a 4-membered ring. And then we went to the other way. Instead of a 5-membered ring, we had a 6-membered ring. There's also a 7 and an 8 that we did. And there's a 3. So the 3 is what we're looking at. That's my little pet project, is I'm trying to get the 3-membered ring we want to form now. So this was really cool. It opened up a whole thing, and every one of these has that chiral carbon in it. So any one of these could be a catalyst that might give us a chiral product. Now, the other side of that, how many of you have taken ibuprofen? Right? You feel bad, you take some ibuprofen, some Motrin, Advil, whatever, right? So that has those non-superimposable carbons in it somewhere, right? So there's two, when you take a Motrin, there's 2 different molecules in there. One of them, I think it's the S, fixes your headache, right? The R one doesn't do anything. It's inert. It'll slowly interconvert, but slowly. So when you take a Motrin, right, half of it just gets excreted as it doesn't do anything, right? Which is, okay, it also doesn't hurt you, but fine. Back in the 60s, there was something that would hurt you, a drug called thalidomide. Same thing, it's got an R and an S. The R is a anti-nausea drug for pregnant ladies. Sounds like a great thing if you have morning sickness. The S version causes horrible birth defects in the fetus. And they also interconvert, right? So being able to make one over the other potentially is a big deal. In the case of that drug, it wouldn't have mattered because the R would convert to S in the body and so forth. But it's a big deal. I think there's a bullet point later on here that most of the drugs on the market now have at least one chiral center in them. So being able to form that bond if you're a drug person is a big deal. All right. So we had to go do the catalysis work because now we've made cis, and we're going to prove it. Cis, I've got an X-ray structure, I know it's cis, but we should be able to do some, like in my world, do some stuff with it. So we went to they do all this fun stuff, all the drugs, here it is. So the chiral centers, they're hard to synthesize, right? You can't just, I mean, you can get them, but If you do it by dumb luck, then you got to figure out how do I separate the good stuff from the bad stuff so that thalidomide doesn't happen again. So it's important to do this. So we go to the literature, and we just, this was just kind of the eeny, meeny, miny, moe part, which actually does happen a lot in chemistry. Like, I'm just going to go, that one, right? So I went to the literature, and I picked a popular reaction that a lot of folks were doing to evaluate catalyst activity. There's no rhyme or reason to this reaction. It's just a popular one that is easy to do, and it's not air sensitive. In fact, this one requires oxygen to even work. So when you do this, the reason this one is cool is you take this thing and you take that thing and when you make it, so this product is your chiral product, so you can make R and S. And you can also do some other stuff where you form this double bond and you put these things on the same side of the double bond, which is also called cis. You can do the same thing down here, we call that Z. You can do the same thing here where they're on opposite sides, so that's trans, or the E thing. And you can homocouple this thing, and you can make biphenyls, which are good for like fire retardant kind of stuff. Those of us that are children of the 70s, your pajamas were soaked in like tetrabromo biphenyl, and we're all still fine, so fun stuff. So again, we did this, again, no rhyme or reason. We do this because this is a pretty standard reaction. We can say, hey, when we use this model reaction, we get 40% activity, we get 80% activity, and we can compare that to some of the gold standard catalysts out there, which I will admit, these compounds they give what we call modest activity. The really good ones give you 98, 99% selectivity. The stuff that my group is working on, the best we've ever had is 60%, which is commercially non-viable, but it's still good basic science. All right, so along the way, a little cautionary tale pops up. We're making all this stuff, right? We're cranking data out. This is fantastic. And so we get a crystal structure that looks like this thing on the left with a flashing arrow at it. We go, holy crow! We made a stacked palladium dimer with a palladium metal bond, which was nuts. We go, this is super cool. Like this is a top tier publication. But we can't just take the one piece of data. We've got to do some other work. So we said we've got to make sure that there's not something weird going on. So we stuck it in another instrument that does some thermal characteristics. And what we found out, unfortunately, was all that happens is when the crystal collapses, when it shrinks, when you cool it down to the diffractometer, it brings two molecules just close enough that the software goes, oh, the distance between those is within the limits of what we would expect for that metal-metal bond. So it draws it in. It says, you must have the bond. And it's like, dang it, no, you really don't. Because when you heat it up, that's this little hump right here. When you heat it up, it just goes, and it pops back open just enough, and then it says, no, now you're outside the ring. So the weird part of that was you do your crystal structures at 100 Kelvin. You almost never do them at room temperature because the data looks crummy. Well, this one we did do it at room temperature to prove that, yeah, when you heat it up, now they expand. And we're talking expansion of like angstroms. So my chemistry kids, you guys know, science colleagues, you guys know, the difference is just a couple of angstroms, right? So it doesn't really change. So you just, you gotta take everything you do with a grain of salt. And verify. What's the old Reaganism? Trust but verify. There you go. So what are we doing now? Now we're still doing the same palladium. We've got platinum and gold. Try to run through some of this. We're looking at molecules that have fluorine, sulfur, and bromine on them. Fluorine is good for blood-brain barrier transport, and then sulfur and bromine have some other antimicrobial and neuro effects. So I'll throw some structures up here. So my students, past and present, Justin was working on these couple of compounds. This was a sulfur-containing one. Over here, this one was cool. You could make it, and it would last for about 2 days. And you get the mass spec, and go, aha, I made it. And then it would, over the course of 48 hours, it would turn into this brown schmutz with metal plated out onto the flask. And it was like, so it's just not stable. And that's because of those nitrogen double bonds. There's Jillian. She graduated, I should say 25. She graduated last year. So she was doing some stuff. National Cancer Institute is really interested in things that have nitrogen in them or heteroatoms in these rings. So she was interested in doing cancer stuff, so she said, hey, can I find something? So she went out and identified these things, these ligands to stick on the metals. And this was one example of that. And so we made the compounds, and this is one where we're in that realm of like, we just are waiting for them to crystallize. We know we've made the compound, but I can't send them off for testing until we get a crystal structure and make that happen. So then she switched over and did some stuff with histidine. This was just because she was bored. The spectroscopy is not so important. The cool thing with this one was it turns into like this gelatinous, like optically crystal clear, but there's like this jello in the tube. It's really cool. We have no idea what's going on with that, but we're still trying to figure that out. Cullen was doing the same thing. He wanted to do fused ring systems, and we found the same thing with the fluorine on it, so he was doing that. Again, we've made the complex. We know we have it, but we don't have crystals yet. So we're kind of in limbo on that one. And then, shoot through my current students, Whitey, over there, he's going to be looking at a platinum compound, where we've got this position is substituted. We're going to start with a hydrogen, and then we're going to do a chlorine, because we can buy these two. And then we may have to make this to do the same kind of thing with the fluorine stuff too. And then Parker is going to do our gold chemistry. First time we've done gold, but I like this one a lot because this really does look like cisplatin with 2 chlorides on it. Here's your metal center, whatever we're going to hang off this side. This has also got a fluorine, so if this has some anti-cancer activity, if we can get it to crystallize, that could be significant, having the fluorine on there. And honestly, that one should crystallize easier because you've only got you've got different things on both sides of the metal. So symmetry tends to make things not want to crystallize sometimes. They kind of get in the way. So this one will be very interesting. They've both completed background reviews and searches and experimental plans. And so we're going to get these kicked off here. I have them both again next semester. So we're going to get the synthesis kicked off before the holiday break, and then hopefully get some data collected while we're all eating turkey and fun stuff. I'm out of time. So I'm going to stop there. I didn't get to talk about my biological stuff. I'll come find you guys later. Questions? Comments? Concerns? We'll pretend like it's a classroom. What you got?
Is the part of the talk that's missing where you talk about like the Kirby-Bauer and the tumor line testing?
Let's see some data.
Yes.
There we go. So we tested, we didn't do this here, right? But this is some of the testing that we did down at VT. With some of the palladium compounds, so alanine, proline, azetidine, and phenylalanine complexes tested against, I vaguely remember what those bugs are and what they do. I think they're mycobacteria, and they were non-pathogenic stand-ins for things like tuberculosis and things. I think that's what we were going for with that one. And then MRSA, because apparently every lab at Tech has MRSA samples everywhere, so you can test against it real easy. And of course, so we're not going to do that here anyway because it was all inactive. But apparently, against some of these mycobacterials, there is some activity. And what's the cool thing to note here is against these two, only the ones with ring systems are active against everything. These that don't have fused ring systems don't really do. And then hopefully we get some more crystals grown and we send them off to NCI. But that's really the new stuff that we're working on. So I did get a tiny bit of that. I have to keep Professor Brooks happy. Any other questions? Things like, I hope most of it didn't go over the top of heads. Happy to, if you have questions, you want to come find me in my office, happy to talk about what we do. So. Thanks.